Today we're diving into something called algebraic systems theory. And the best way to think about it is as a blueprint for a machine that you haven't even built yet. So let's just jump right in with a question. Imagine you're an engineer. How would you prove with absolute certainty that a machine is going to work perfectly using only the math on a piece of paper before a single bolt has been turned? Well, that's the exact problem this whole field is designed to solve.
All right, so here's our game plan. First, we'll talk about the machine itself, what these linear systems really are. Then we'll look at the blueprint, which is this whole new algebraic way of looking at things. After that, we'll check out the toolkit, the actual tools of the trade. We'll see what the inspection tells us about the machine's most important features, and finally, we'll put it all in the library to see how it fits into the bigger picture.
Okay, let's get started with section 1, the machine. When we talk about linear systems, what are we actually talking about? Well, you can think of them as the invisible engines that are kind of secretly running our world. At their very core, these are just systems whose behavior can be described with a specific kind of math, linear equations. Now, I know that sounds super abstract, but it covers a huge range of stuff. We're talking about everything from the signals zipping through an electrical circuit, to the models that predict our economy, or even how a satellite stays in orbit. Now, for these systems to be predictable and, well-behaved, they have to play by some really strict rules. One common type has to have 4 key traits. First is linearity, which just means its outputs are proportional to its inputs. Then there's time-invariance, meaning its behavior doesn't just randomly change over time. And then there are these other 2, jet closeness and jet determinedness. Don't worry about the names. What they do is just make sure the system is complete and mathematically consistent. You can think of these 4 rules as the laws of physics for our machine. If they're not there, the blueprint is just fundamentally broken from the start. And that brings us right to the blueprint. See, instead of just plugging in numbers to find one specific answer, this approach takes a huge step back. It's about looking at the deep, fundamental structure of the system itself. So the formal definition is that it's the study of the underlying algebraic structures, the mathematical rules and relationships that define how these systems work. And what's so cool about it is that it acts like this amazing bridge, connecting the super abstract world of pure math with the very real, practical world of engineering and science. This quote here really just nails it. If a linear system is a machine, algebraic systems theory is the blueprint of its fundamental components and mathematical connections. So you see, it's not just about what the machine does, it's about having the mathematical proof that shows why the design itself is sound from the ground up. So, if you're an engineer holding this blueprint, what tools are you using to analyze it? Well, you can forget about wrenches and screwdrivers. Your toolkit is full of incredibly powerful mathematical instruments. Let's look at 3 of the big ones. First up, you've got module theory. Think of this as a kind of universal language that lets us describe a system's core properties, even for really tricky systems that have time delays. Then there's geometric algebra. This one is all about visualization, using shapes and spaces to really get a feel for the system's hidden structure. And finally, you have the heavy lifter, Groebner bases. These are basically superpowered calculators, an engine for solving the gnarly equations that pop up all the time.
Okay, so we've got the blueprint, we've got the tools, so what? What can this inspection actually tell us? What are the really big make-or-break questions we can answer just by looking at the design?
Well, it boils down to 2 absolutely critical properties, controllability and observability. Controllability asks a simple question. Can we actually steer this thing wherever we want it to go? Is it fundamentally under our control? And observability asks, can we figure out what's happening on the inside of the machine just by looking at what it's spitting out on the outside? I mean, think about it. A system you can't steer is useless, and a system you can't understand is just a dangerous black box. These 2 properties are pretty much the bedrock of good system design. All right, let's zoom out for a second and see where this all fits in the bigger picture. This field isn't an island. It's actually part of a much, much larger library of ideas about how we can formally understand complex systems. As you can see, algebraic systems theory is part of a bigger field called axiomatic systems theory, which tries to find the rules for all systems, not just linear ones. It also crosses paths with something called the behavioral approach, which focuses more on a system's possible outcomes. They're all part of the same grand project, really, trying to create a universal language to describe complexity. So if you take one thing away from all this, it should be this. Algebraic systems theory isn't about calculating a single answer for a single problem. It's about something much deeper. It's about using the power of abstract math to prove that the very design, the integrity, the logic of the system is solid before you ever even think about building it. It's about proving the blueprint is perfect. And that leaves us with a pretty fascinating question to chew on. We've got this incredible algebraic blueprint for the linear systems that power so much of our world. But when we look to the future, to things like AI, quantum computing, or complex biological systems, what new kind of math are we going to need to invent to draw the blueprints for them?